Hi and welcome back. This is an important lecture today for two reasons. One is we are starting a brand new chapter. Secondly, we are starting the all important calculus today. I'm Rajesh from Cloud Tutors. Let's get started. So, there are three important parts of calculus, some of which you study in grade 11 typically, and some of which in grade 12. So we are going to start with the first of the many topics in calculus. So the first topic in calculus that we are going to be discussing at length is limits. What are limits? How do we define them? I want to spend some time giving you a visual and intuitive understanding of limits, as well as the mathematically rigorous definition of limits. Then we'll talk briefly about the application of limits, and if you are familiar with this lecture series at all, you will know that it is important to appreciate the practical applications of any concept you learn, whether it is mathematics or science, with the belief that every concept has practical applications. So I'll spend a few minutes talking about applications of limits, then the concepts of right and left hand limits, and then evaluation of limits. And that will lead us to different patterns, whether they are algebraic expressions, trigonometric expressions, inverse trigonometric expressions, logarithmic, exponential functions. We need to be able to find the limits of every kind of function. And that is where the bulk of the time in this series will be spent. And of course, all the practice questions drawn from multiple sources, multiple boards as well as competitive exams. So that's going to be the structure on this series on limits. So let's get started. Definition of limits. So it's important to conceptually understand what limits are. And I feel that many students, while they understand the mechanics of solving problems and they know the formulae and they know how to go about problems, they fail sometimes to appreciate the concept of limits. So let's spend a few minutes talking about that. Now let's look at this graph. Now this is a parabola, and I've shown you the graph of a part of the parabola, and it's an y is equal to x square something, a quadratic function. Now let us see what happens to the value of the function f of x as x approaches 2. Right now x is at 1.8. And what happens to the function f of x as x gets closer and closer to 2? And that's the question. So when x is 1.8, f of x is 3.0, which means when x is somewhere over here, this is 1.8, then f of x, which is somewhere over here, is 3.04. What happens when we increase x by 0.1? Goes to 1.9. X is even closer to 2 now. F of x goes to 3.51. We increase x just a little bit more. It becomes 1.95, inching closer to 2. And f of x becomes 3.7525. So all I'm doing is substituting different values of x in this function, whatever that function is, and getting the corresponding values of f of x. You make x 1.98, you get f of x 3.9004. Increase it to 1.99, f of x is 3.9501. And then f of x, x is 1.999, and f of x is 3.9950. So what's the point of all this? The point is, as we start from somewhere here, we started with x is equal to 1.8. We started to the left of x is equal to 2. We started to the left. And as x approached 2, we went in steps of We went from 1.8 to 1.9, then to 1.95, and so on. As we went closer and closer to x is equal to 2, you could see that the value of f of x approached 4. And this is a very simple example, and it is easy to see why f of x approaches 4. So as x approaches 2 from the left hand side, f of x approached 4. And yet again, x becomes 1.9999 and f of x becomes 3.9995, closer and closer to 4. So what we can say in this context is, as x approached 2, f of x approached 4. And you can see why that statement can be made. Let's do the other thing. Let us start from the right side of 2, which means we are starting with values of x which are greater than 2. And then we are going to decrease those values of x and approach x is equal to 2 from the right hand side. And what happens to f of x in that case? When x is equal to 2.2, f of x is equal to 5.04. By the way, this function was x squared plus x minus 2. I did not write the complete function at that time. So with the same function, we are starting with values of x on the right side, greater than 2. And we are trying to examine what happens to the values of f of x. We start with x is equal to 2.2 and we get f of x 5.04. And you can use this function, substitute these values of x in it and see, examine this for yourself. X becomes 2.1, so it goes closer to x is equal to 2, and f of x becomes 4.51. X becomes 2.05, even closer to x is equal to 2, and f of x becomes 4.2525. At x is equal to 2.02, f of x is 4.1004, and so on. As x goes closer and closer to 2, you can see that f of x approaches 4. Now what we did, we did two things. One is in this function, in this slide, we approached x is equal to 2 from the left hand side and gradually increased the value of x until it got closer and closer to x is equal to 2. And in this slide, we started with values of x greater than 2 and approached x is equal to 2 from the right hand side. And in both cases, the conclusion clearly is that as x approaches 2 from either side, the left hand side or the right hand side, the value of f of x approaches 4. What about a graph like this? Now you can see that x is equal to 4 is an asymptote to this, y is equal to 4. This line here is the line y is equal to 4, and y is equal to 4 is a horizontal asymptote for this graph. And you all know what the meaning of asymptote is. The graph approaches the asymptote, it gets closer and closer to it without ever touching it. That's an asymptote. Now it means that as x increases, the graph of the function gets closer and closer to the asymptote, which means that as x approaches infinity, then f of x approaches 4. And it's very easy to see in this graph why that is the case. In this case, we can say that as x approaches infinity, y is, or f of x is equal to 4. So I'll give you the formal definition of limits and then several examples to make sure you understand this definition. So if f of x is a function defined around an interval x0, we say that the limit f of x as x approaches x naught is L. If for every epsilon that's greater than 0, positive value of epsilon, there exists another positive value delta, such that for all x, such that the difference between x and x naught is less than delta, the difference between f of x and L is less than epsilon. And that can be represented in the form of a limit. Now, what does it mean? It means that I have a function f of x, and I want f of x to get very close to a fixed value L. I want to take the value of f of x very close to L. How close should I take it to L? Well, I want to take f of x so close to L that the difference between these two becomes very, very small. It is smaller than an arbitrary positive value called epsilon. If epsilon is a very small value, very small positive value, then I want the difference between the function and L to be smaller than epsilon, which means that f of x has gone very close to L. If I want to do that, then if there exists x such that the difference between x and x naught is small, smaller than the positive value delta, such that the function f of x is sufficiently close to L. There will exist such an x. You can get as close as you want to the value L, because there will be some value of x which will make sure that the difference between f of x and L is small enough, smaller than the value epsilon. That's what it means. And we have seen that in the previous example. You can see that here. I want f of x to be within 0.02 or let me say 0.04 of 4.00. I want f of x to get so close to 4 that the difference between f of x and 4 should be less than or equal to 0.04. Yes, well, there is a value of x here. We can see that there is a value of x which will ensure that the value of f of x is close enough to 4. So you can pick any value like 4. You can find a corresponding value x such that your function gets to within that range of the fixed value 4. And that's the definition of limits. Graphically, this can be represented as follows. There exists a value x naught, and I want to define, and of course this is f of x, and I want to, and let's call this L. This value here is L, and I want f of x to get very close to L. What does very close mean? That means I have to be within this narrow boundary, narrow range here on either side of L. So L is here, and this is the narrow range in which I want to make sure f of x lies. How can I do that? By making sure that the value of x is in that narrow range over here on either side of x naught. So if x is between x naught minus delta and x naught plus delta, if x happens to be between those two values, then you can see from the graph that f of x will be within these two values. And that is what the definition of limit is. So you can take f of x as close as you want to a specific value L, and there exists some value of x which will let you do that. Now let's briefly talk about left hand and right hand limits, and we will talk at length about these later. So left hand and right hand limits. So you consider this function here. Now clearly it is a discontinuous function. There is one part of the function which goes like that, and the other part of the function which goes like this. Now this is a function. It satisfies the vertical line test. It is a function, but it is a discontinuous function because one part of the function goes like this, and then there is a discontinuity, there is a break, and the rest of the function goes like this. This part of the function is for, if this is 1, 2, 3, 4, 5, 6, etc. This part of the function is for x is greater than or equal to 5, and this part of the function is for x is less than 5. So two different graphs for a single function because there is a discontinuity. Now what happens when we take the limit of this function, the limit of this function, x tends to 5, x is approaching 5. What is the limit of the function f of x as x approaches 5? Let's consider approaching 5 from the left hand side and the right hand side. First, the left hand side. You're approaching x is equal to 5 from values of x which are lower than 5. If we start somewhere here, let's see. For this value of x here, the corresponding value of f of x is here. For this value of x here, the corresponding value of f of x is here. For as you go closer and closer to x is equal to 5, you will see that f of x approaches the value 5, and that's very easy to see why. The graph is heading towards 5. So as x gets closer and closer to 5, f of x gets closer to 5. What happens when you approach 5 from the right hand side? You start from somewhere here, now you approach x is equal to 5 from the right hand side. You can see that as you approach x is equal to 5 from the right hand side, the value of f of x remains at 2. It doesn't change. So the value of f of x as x approaches 5 from the left hand side is 5, and as x approaches 5 from the right hand side, it is 2. And therefore we say that the limit of the function as x approaches 5 is not defined, because you should get the same value whether you approach x from the left hand side or from the right hand side. And clearly in this example, those two values are not the same. And these examples are important. And in this example, I'll illustrate the same point to you even more clearly. So it's very important to understand these left hand and right hand concepts and to understand when a limit is defined and when it is not. Is also understand the difference between the value of the function and the limit of the function as x approaches a certain value. So let's understand all of this clearly through this example. So take a look at it. So below is the graph of f of x. So clearly it's a discontinuous graph because there is a big break here. There is a graph which goes here and then continues from here. So it's a discontinuous graph. It doesn't matter. For each of the given points, determine the value of the function f of a as well as the limit of the function as x approaches a. Now the first value is a is equal to -3. So what happens? We need to find these two. we need to find this, and we need to find the limit of the function as x approaches negative 3. And let's see if there is a difference. Now f of minus 3 is this value here, because it's clearly given there with the notation that the value of the function at x is equal to negative 3 is 4. So let me write it here. This is 4. But what about the limit of the function as x approaches 3 or negative 3? So when you approach negative 3 from the left hand side, from values of x lesser than negative 3, you will see that the function approaches the value 4 here. As you approach x from the left hand side, the value of the function approaches 4. And as you approach x is equal to negative 3 from the right hand side, you can see that the value of the function approaches negative 2. So the value of the function as x approaches negative 3 from the left hand side is different from what happens to f of x when you approach x is equal to negative 3 from the right hand side. And therefore we say limit does not exist. And it's very important to realize that while the function is defined according to the graph, f of negative 3 is defined and it's 4, but the limit of f of x as x tends to negative 3 is not. And these distinctions are very important to understand before we get to harder questions. What about the next value of a? What we need to do is to find f of negative 1, because the next value of a is negative 1, and we also need to find the limit of f of x as x tends to negative 1. These are the two things we need to do. So f of negative 1 is, if you look at the value of the function, it is here. You can see the graph. This notation indicates that the function is not defined for x is equal to negative 1. That's what it says in the graph. For the actual value of f of minus 1 is over here. And we know that, therefore, it is 3. F of negative 1 is 3. Now what happens when you approach x is equal to negative 1 from the left hand side and the right hand side? When you approach x is equal to negative 1 from the left hand side, the value of f of x approaches 1. And when you approach x is equal to negative 1 from the right hand side, even then the value of the function approaches 1. So whether you approach x is equal to negative 1 from the left hand side or from the right hand side, you can see from the graph that the value of the function approaches 1. Therefore, now this is another situation which is also possible. This is a situation where f of x is defined, and in this case f of negative 1 is 3. The limit is also defined. Limit of f of x as x tends to negative 1 is 1. But these two are not equal. The limit is not the same as the value of the function at that point. This is the second possibility, also illustrated in this graph. Now let's look at what else can happen. Let's look at the third value of a and see what's possible. Now we are talking about a is equal to 2, and so we need to find f of 2, and we also need to find the limit of the function as x approaches 2. And let's see what happens here. Now when x is equal to 2, you look at the graph and you see that hollow circle there. It indicates that the function is not defined at x is equal to 2. Why is it not defined? It's hard to say, but the graph clearly says that the function is not defined at x is equal to 2. So we can say is not defined. What about the limit as x approaches 2? Now as you approach x equal to 2 from the left hand side, the value of the function approaches 1. You can see that it approaches 1. And as the value of x approaches 2 from the right hand side, also you can see that the value of the function approaches 1. This is a situation where the function is not defined, but the limit is. So what we have seen with just these graphs, or this graph, are three situations. One is the function is defined, but the limit was not. Second is the function and the limit are defined, but they have different values. In the third situation, we saw that the function is not defined, the limit is. Let's see what happens in the fourth situation. The fourth situation is where a is equal to 4. So we need to find f of 4, and we also need to find the limit of f of x as x tends to 4. As x tends to 4, you can see that the value of the function is 5 over here. You can also see that as x approaches 4 from the left hand side, the function approaches 5. And similarly, when x approaches 4 from the right hand side, the value of the function approaches 5 again. So whether you approach x is equal to 4 from the left hand side or the right hand side, the value of the function approaches 5. So the limit exists and is equal to 5. So what we see in the fourth situation is that both function and limit exist and they happen to be equal. Now what I have illustrated with this example are many things. The concept of approaching a value from the left and right hand sides, the condition under which we can say that the limit is defined, and the four possibilities. Function exists, limit doesn't. Limit exists, function doesn't. Both of them exist but they have different values. Both of them exist and they have the same value. All four situations are possible. Having spent all this time on explaining the concept of a limit, let's try and talk about very briefly the application of limits. Where are they used? Why do we have to know about this concept? In a typical academic year, a lot of time and effort is spent on limits, and that forms the foundation for calculus. Why study limits? Well, here are a few reasons why. A limit allows us to examine the tendency of a function around a given point, even when the function is not defined at the point. You may be studying the behavior of any system, any complex system. You have modeled it mathematically. You are studying it. And you can study how the system behaves near a given input, even if the function is not defined at that specific input. Limits are also important because they serve as the basis for the definition for what is to come later. So later in calculus we talk about derivatives and integrals, and an understanding of limits is essential, because when we talk about limits, you begin to understand the concept of x approaching a specific value a. What does it mean? And finally, you also begin to understand through the discussion on limits the concept of getting arbitrarily close to a point. And in several of the examples I have discussed so far, you've seen that we are getting closer and closer to a specific value of x. And then we are seeing how f of x behaves as x gets closer and closer to a fixed value. How close do we have to get? Well, it is not known. As close as you can, arbitrarily close. You can get extremely close, infinitesimally close. And as you get closer and closer, you can observe the behavior of the function and see what happens. All of these may seem a little abstract, but they form the basis for two other extremely important parts of mathematics, namely derivatives and integrals, which will come later in our series. So let's do a few practice questions, and these are simple questions, no doubt, but they allow you to further cement the understanding of limits. So let's get started. So limit of x square minus 3x plus 2 divided by x minus 1. And clearly, if you simply substitute x is equal to 1 in all this, the denominator becomes 0, and therefore this entire expression is undefined. So clearly, if this entire expression is f of x, we are not finding this. We are not trying to find f of 1, because f of 1 is not defined, because the denominator becomes 0. What we are trying to find in this exercise is what is the value of this expression as x gets closer and closer to 1, but never equal to 1. It's like saying what happens when x becomes 0.099999. Is it equal to 1? No, but you're getting very close to 1. What happens when x is 1.00001? Again, not equal to 1, but extremely close to 1. And you're observing what happens to this expression as a whole as x gets closer and closer to 1. How do we do it? Let's try to simplify this. This is equal to limit of x approaches 1, and you can factorize the numerator and write it as x minus 1, x minus 2. All I did was factorize the quadratic expression which is in the numerator, and now I can cancel this. Now it looks like a very simple and obvious step to cancel the two terms, one in the numerator and one in the denominator, x minus 1. But there is a concept that you should appreciate here. If x was equal to 1, then x minus 1 would be equal to 0. You would not be able to cancel it if these terms are 0. You're able to cancel the term in the numerator and the term in the denominator because they are non-zero terms. X minus 1 is not 0, and therefore you can cancel it. What you're left with is x tends to 1, and that is negative 1. So as x approaches 1, the value of the given expression here approaches negative 1. And you can also be sure that you could approach x is equal to negative 1 from either the left hand side or from the right hand side. In either case, the limit or the value of the function will approach negative 1. That's the value of the limit. A slightly different example. Evaluate the limit. Limit of x tends to 1 of x cube minus x square log x plus log x minus 1 divided by x square minus 1. And that can be written with a little bit of simplification as we'll group two terms. We'll combine x cube minus 1, and then we will combine so I have combined x cube minus 1 together, these two terms, and then these two are combined together as well by taking log x out as a common term between those two divided by x squared minus 1. that becomes limit of x tends to 1. X minus 1 is common to both those terms, so it becomes x square plus x plus 1. X minus 1 is common to both the terms in the numerator, hence I could do this, and therefore it's the limit of, as x tends to 1, you can end up with x square plus x plus 1 minus log of x Now this is easy to compute because we can actually substitute the value x is equal to 1 in this and get the final answer. It becomes 1 plus 1 plus 1 minus log of 1 multiplied by 2. This is the numerator, divided by 2, and that gives you 3 as the final answer, the final limit of this expression as x tends to 1. Realize that you can't substitute x is equal to 1 in the first step, because then again the denominator becomes undefined, or the denominator becomes 0 and the expression becomes undefined. Therefore, we went through a few steps of simplification before we substituted x is equal to 1. So the limit exists and it is equal to 3 divided by 2. What about this one? Find if this has a limit. So the important thing to realize is in some of the questions they may ask you to determine if a limit exists, and if so, find it. So here we need to find whether a limit does exist. Now from the graph it's possible to tell, but let's not do it that way. Let's do it slightly differently. As you approach x from x is equal to 4, remember we are approaching x is equal to 4, let's approach it first from the left hand side. So x is lesser. If I pick an arbitrarily close value of x, close to 4, then you can see that as you approach 4 from the left hand side, the value of x is less than 4, and therefore what happens is it becomes limit of, as you approach it from the left hand side, x minus 4 is a negative value because x is less than 4, so it becomes and that is limit of x tends to 4 negative 1. And you could tell from the graph as well, as x approached 4 from the left hand side, the value of the limit or the function is approaching negative 1. What if you approach 4 from the right hand side? Over here you start approaching x is equal to 4. You can see that the value of the function is here, and so x is greater than 4 in that case. So this is just x minus 4 by x minus 4. So as you approached x is equal to 4 from the left hand side, the function approached negative 1. As you approached x is equal to 4 from the right hand side, the function approached positive 1. And since these two values are not equal, the limit does not exist. We can leave it at that. Find the limit of this expression. Now so we are doing a bunch of practice questions related to algebraic expressions. We will of course later get to trigonometric and exponential and logarithmic expressions as well. So for the moment we are looking at some algebraic expressions. Here is the next one. Limit as x tends to 2, x square minus 4 divided by square root of 3x minus 2 minus square root of x plus 2. So the convenient way to do it would be to rationalize the denominator. Let's multiply and divide the entire expression by the conjugate of the denominator. So how do we do that? Let's just write the expression out like this. This is our expression. So I'm going to multiply it and divide it by like that. So by the same value, and it happens to be the conjugate of this denominator here, and that becomes equal to x square minus 4 multiplied by 3x minus 2 plus square root of x plus 2. That's the numerator divided by 3x minus 2 minus x plus 2. That's the denominator. And so on further simplification, it becomes x square minus 4 square root of 3x minus 2 plus square root of x plus 2 which you can simplify finally to look like this: x plus 2 like that. Now at this stage we will be able to substitute x is equal to 2 in the expression, because it is defined at when after we simplified it to look like this. So if I now calculate the limit, it becomes 4 multiplied by square root of 4 plus square root of 4 divided by 2, and that is 4 multiplied. So a limit does exist and it is equal to 8. So once again, before we could substitute the value x is equal to 2 in the expression, we had to simplify it so that the expression is defined. If you substitute x is equal to 2 in the very first step, then the denominator is undefined. So you can't do that. So we had to rationalize the denominator by multiplying it by its conjugate. And once we did so, we could then substitute x is equal to 2 in the expression and get the answer. So that's that. Now there is an important result to prove, and this is a useful result because quite a few questions in limits can be answered with that result. So what does it say? It says that if the limit, if the function is of this form, x to the power of n minus a to the power of n divided by x minus a, then the limit of that function as x approaches a is given by n multiplied by a to the power of n minus 1. And this result is also useful in the next chapter on derivatives, as you will see later. So how do we prove this? It's quite simple. X to the power of n minus a to the power of n can, and divided by x minus a, can actually be written as x to the power of n minus 1 plus a multiplied by x to the power of n minus 2 plus a square multiplied by x to the power of n minus 3 all the way up to a to the power of n minus 1. So these are the terms that you will get when you divide x to the power of n minus a to the power of n by x minus a. So what we need to find out is really the limit as x tends to a, all these terms. And how many terms are there? there are n terms here. Here there are n terms. So what it becomes is, in every one of these n terms, I could substitute x is equal to a. So what do you get? You get a to the power of n minus 1 plus a multiplied by a to the power of n minus 2 plus a square multiplied by a to the power of n minus 3, all the way up to a to the power of n minus 1. Now you realize each of these is n minus 1. So how many such terms are there? I told you there are n terms. So this really is n multiplied by a power n minus 1. That's the result. So this is useful, like I said. Let's see first by looking at this particular question. Now we are going to do it using two different approaches. First is, let's do the familiar trial and error method. Let's keep applying different values of x as x gets closer and closer to 2. Then let's see what happens to this function. And then we will use it, then we will solve it using this formula and see what we get. Two approaches. Right? So now, this table, you realize we are getting closer and closer to x from the right hand side. We are approaching x is equal to 2. Started with x is equal to 2.5, then x became 2.1, 2.01, 2.001, 2.0001. So you're approaching x is equal to 2 from the right hand side. And what happens to the function of x? It starts at negative 3.38 and it is getting closer and closer to negative 3. So you can say that as x approaches 2 from the right hand side, f of x is approaching negative 3. What happens when you approach x is equal to 2 from the left hand side? We start now from the left hand side. Remember, x is equal to 1.5. And then we keep increasing x. You get x closer and closer to 2. And see what happens to the function of x. So when x is 1.5, f of x is negative 2.64, it becomes negative 2.92, and so on. And you can see that as x gets closer to 2, f of x gets closer to negative 3. So the conclusion here is, whether you approach x is equal to 2 from the right hand side or from the left hand side, you can see that the function of x approaches negative 3. So we can safely conclude that the limit exists, the limit for the function as x approaches 2 exists and is equal to negative 3. That we could tell by just arbitrarily applying different values of x and getting it closer and closer to 2 and seeing what the value of the function is. Now let's do it in a more rigorous way. How would we do that? Remember, we have a limit of x tends to 2, 8 minus x cubed divided by x squared minus 4. Earlier we did it by applying different values of x. Now let us use this. This is the result we saw a few minutes ago. So how do we use this? Let's first consider limit of x tends to 2, 8 minus x cubed by 2 minus x multiplied by 2 . I will rewrite it slightly differently. Negative of x cubed minus 8 by x minus 2, x minus 2 by. So I have multiplied and divided by x minus 2. So we have a x minus 2 in the denominator and an x minus 2 in the numerator, so nothing has changed. So that will allow me to use this result separately, once for this part and once for this part. So what happens when I just consider this part now? So limit of x tends to 2, negative x cubed minus 8 by x minus 2 is of this form, and therefore I can write it as limit of x tends to 2, negative x cubed minus 2 cubed by x minus 2, and that is equal to 3 times 2 to the power. So that is one part of the limit. What about the other part of the limit? Well, x minus 2 is the numerator, x minus 4 is the denominator, so we end up with, this is 4 can be written, you realize, as 2 square, and this becomes 2 multiplied by 2 to the power of 2 minus 1, that is 1 divided by 4. And when you look at these two, and you multiply negative 12 by 1 by 4 to get the final limit, you will end up with negative 3. So the limit of this entire expression becomes minus 12 multiplied by 1 by 4, which is exactly what we got by applying different values of x earlier. So that was an application of this result. So what we have done today is we made a start with the concept of limits, which is a very important concept, especially in the context of calculus, especially because we are going to deal with derivatives and integrals in later lectures. And there are numerous applications in science and technology for all of these areas of mathematics. So it is vital to understand the concept of limits. So I spent quite a bit of time defining limits, giving you several examples of how what it means to find the behavior of a function as x approaches a specific value. And I've illustrated these concepts with numerous examples. So this was the formal definition of limits. So we went through that, and I explained to you with a graph as well what this definition means. This was the diagrammatic representation of what the definition of limit is. So what we'll do in later lectures is look at other results on limits with trigonometric and exponential and logarithmic expressions. Today we focused largely on algebraic functions. So let's look at other kinds of functions in later lectures, and of course much harder questions will follow. Thank you for watching.